Hello, everyone. Thanks for joining the seminar today. I know it's a bit late than our usual time, but thanks for joining. Let me introduce you today's speaker, Salvador Navarro-Martinez, who earned his PhD in aerospace engineering from the University of Southampton in 2002, before moving to Imperial College London, where he obtained a Royal Society University Fellowship on spray atomization, and where he's now a reader in the Department of Mechanical Engineering. His research lies in the broad area of computational modeling of thermofluids. He has been a consultant fluid dynamics expert in forensics, and today he's going to talk about modeling fluids in forensic science. So for all the detectives in there, pay attention. Over to you, Salvador.
Okay, so good evening, everyone. So good morning for me, but thanks for the intro and the invitation. It's a pleasure to be here. So I'm going to talk a tiny bit about myself because I think background is important in this case, especially in a talk like this. So I'm a mechanical engineer, and my background is in, as they say, in turbulence modeling of reactive flows. I am a hardcore modeler, so I like deal with equations, modeling new terms, complex models. One may say the more complex, the better. And today is a bit different. So today I'm going to present forensic science. This is a very applied, it's a very multidisciplinary cases. And the kind of questions I always ask, I get asked is, what turbulent flows and forensic science have to do with each other? How can you use turbulent flows in a criminal investigation? A good salesman will tell you that a lot, they're very important, but okay, it depends on the case. It's not common. It's rare. They are not universal crime scenes. So it may be that fluids are involved, but they may not be relevant to the case, or it may not be a big part. So these are particular cases. So before I start, just a warning, these are real murder investigations. So the victim suspects, they have been changed, name changed. Some cases are very generic. I cannot go into details about particular details. I may be vague. The case, of course, are part of larger investigation, so I won't comment on the non-fluids part of the investigation. Okay, so engineering versus forensic science. So as an engineer or fluid scientist, I'm always interested in the research question. For example, how turbulence affect the heat release rate? This question may be simple or not so simple. Turbulence and heat release, it may seem simpler than it is. However, in forensic science, we are often deal with the case question. The question is very specific. In the research, we always aim for a formula, a number, a quantity, correlation, and we can use that to design better system. In a case, the questions are very, very specific. Could Joe have been in the crime scene? This is very specific. They are not interested in a number. It's not 93 or 24, or the drag is 0.2. It's a very, very specific question. So this changes the way you look at things. Maybe you don't want to delve in the turbulence model that you need, but maybe try to give a more conservative approach. One other thing, in engineering problems, questions are usually well posed. From the fluid mechanics point of view, is boundary and initial conditions are well designed. They may be difficult to implement. Turbulent conditions, it may be a pressure wave leaving the domain. These things may be difficult, but they are known to a certain degree. In cases, usually they are very, very uncertain. We don't know where the shooter was. We do not know exactly where the victim was. People lie. Usually people lie all the time, but even more in these kind of cases, because usually they are criminal cases. So while in engineering we do more design, in forensic science we do more hypothesis testing. So we test scenarios. This can have difference when we report the results. So you will see that the uncertainties may be larger, may be different. So sometimes it's very difficult to communicate your results when you, for example, your audience is made out of lawyers. Nothing to do against lawyers, just okay. Contents. I'm going to talk a little bit about modeling fluids in forensics. What are the sort of two common applications? Just briefly, just to give you a context. Okay. And then I'll talk about basically the two sort of areas I have worked, which are smell dispersion and river transport of bodies. And I will do, there is a question. Sorry, there is a hand raised.
Is it? Yes. Julio, you have your hand raised.
No, sorry, no hand raised. It was a mistake.
Oh, no worries.
Okay. Okay, I thought maybe nothing was showing or something.
No,
okay,
it's all right.
So just continue. Okay, so smell and river. So I will present the case and then the methodology. In research, we always tend to do the other way around. We present first the methodology. I'm going to present my wonderful model and then the application. Here is the other way around. We have a case, we have a question, and then we try to find the best methodology that fits this question. Okay, how can we answer this? So, and then I will end up with some conclusions. So, yeah. Okay, before we move on, a quick thing about forensics. Forensics is not like the movies or CSI. There are many things, there are many fields, many people train it in many specialties, from the classic forensic pathologies, DNA analysis, toxicology, ballistics, whatever. There are even art forensics or finance forensics or computer forensics. So most of them are dominated by people doing biology, medicine, chemistry, and these sort of things. There are even people who look about insects that grow in corpses and things very, let's say, weird from a fluid mechanics point of view. There are two fields when fluids is important. Oops, sorry. Yeah, fire modeling and, arson investigations and blood stain analysis. Arson investigations is when they try to find out the causes of a fire. So there are some uses of fire modeling and CFT there. And also in blood stain analysis, which is when they look at blood patterns and they try to find out what happens. I'll show you quickly some examples. Okay, so this is blood pattern analysis. This is when they use blood patterns. Here you can see here some blood stains, and they try to reconstruct what happened. This is not very old. I mean, when I mean old, I think the first empirical study was in 1895, so it's just 130 years old or something like that. And they are usually very empirical. They often classify blood stain into different categories: blood pool, blood flow, transfer patterns, and then they try to see what's going on. So this is just an example in one of the reviews I found. This is basically, you can see a blood pool in the floor. So they say that the interpretation is the victim was stabbed and he was lying on the floor. So then he bleed. Then he got up, and then there was some transfer to the stove, the kitchen stove. This is the AA mark, this very long lines. Then he put his hand, and there was some transfer marks, this labeled AB. And there is blood pattern. Basically, he was bleeding while he was standing up, and then he left. So it's amazing the amount of information they can get based on knowledge and previous knowledge and empirical correlations. They are nowadays a little bit more, let's say, more fluid dynamics analysis. So they try to have some experiments by explaining pigs' blood into surfaces, and they try to use CFD simulation to get a little bit the shape. You can see here the experiments, and here the CFD. And well, based on the shape of the blood, they can get an idea of the trajectory of the blood. You see here you have a blood pattern. They can measure the angle by looking the shape of the blood stain, and they can try to reconstruct the pattern of the blood. So if they have several stains, they can try to see, okay, where the trajectories merge would be for the victim. Originally, they use pure trigonometry using straight trajectories, and of course, the errors are very large. Then they start considering gravity and drag. You will believe that there's still a lot of analysis. It's in 2010. They were still doing a lot of straight trajectories, okay? And things like gravity and drag were not considered. Nowadays, they use even more stuff. They include surface tension. You have to remember that blood is a non-Newtonian fluid. There's several physics, usually it's droplets impacting, fluid impacts, wettability. There is a lot of little consideration. So this is basically one of the biggest application of fluid mechanics in forensic science. The other one would be forensic fire or arson. This is just a case. This is one of the first use of CFD in forensics. Like, let's call it modern CFD. In this case, there was a fire in a prison in Chile. This is like a picture of the one floor of the prison where 80 people died. And I think in this paper, I believe there was one Melbourne co-author, Jose Torero, who was in this paper, where basically they tried to calculate how the fire spread. This was all motivated because there was an accusation against prison guards wondering if they acted negligently or they ignored the fire for long. You see, there was a lot of combustible material, so it was quite difficult to predict the spread of the fire. So I think they did some experiments how the fire was spreading, and then basically they did sort of CFD. You can see here how the smoke was 1 minute after the fire started, and how the smoke was 5 minutes after the fire started. Of course, the validation was weird. There was no experimental measurements. The only thing they know is there was here some windows, and there was some smoke from the window, and there was a CCTV camera that captured that. So they inferred how long was the fire burning before smoke could be seen. So they figured out it's roughly 5 minutes. So see, the idea here is they have a question: how long was the fire? Did the guards act properly? Did they have time to react? The guards were on a different floor, so they have to climb up to open the door for the prisons. So this kind of study somehow motivated my research a little bit, because it's the use of CFD, they use a particular question, they use conservative estimates. I mean, it's clear that it was impossible to model in full detail. You just look at the thing in the prison. How can you realistically pretend to model this? Okay, but they got a decent idea. So that's basically sort of the motivation, and I'm going to present the cases I was involved. So this is my case one. This case is public, so you can go into YouTube and find the nice movies and videos, maybe a bigger report and everything. That was a collaboration I did with Forensic Architecture, which is a research agency investigating human rights violations. And basically, the idea is 2006, shortly after 5, there was a receptionist, 21-year-old, murdered while attending the reception counter of his family-run internet cafe. So this is you see, it's 2006, so there were internet cafes there. That was in Berlin. No one was convicted, and 10 years after, the police archives were open, so then forensic architecture got involved. So they asked me to comment on the fluid points of it. So just to give you a little bit brief of what happened, this is a very close environment. This is a very, very small internet cafe. And you see this is relatively small. I don't remember the size on the top of my head, but you can see there are very few tables. Because it's an internet cafe, they have very precise timings about when people log in and log off, when the calls were connected or not. There was still some call center and some cabins here. So in red is our victim, was on the table. This is like a normal table. And you can see here, 4:30, the victim was alone. And then we have times of people entering and logging into the computer. So AA and EE. So witness in blue, they connect, they log in. I think they were playing Call of Duty. So someone entered here, HC, enter, and they did a phone call. IT, which is going to be our suspect, enter at 4:50 and logs in that computer over here. So then at 54, FH enters and makes a call. And then everything, there is one key minute, you see at 5:01, when a lot of things happen. So FH finishes first call, AT logs out and leaves, HC starts her second call, and at that time, FH and HC heard 2 gunshots. They was not like very loud gunshots. They were like tack, tack. So it was done with a silencer. So it was not something that they startled, but not a very big gunshot. The FH start the second call, and 1 minute later, he exits and the victim is dead. So the key thing is there is basically 1 minute 10 or 1 minute a bit more when AT gets out, he doesn't see the killer or he doesn't see the victim. He claims that he got up, searched for the victim, could not find him, put the money in the counter and left. So in the police reconstruction, there was like a minute. And well, he claims that he did not hear the shots, although the other witness did. He did not smell the distinct smell of gunpowder, and he did not see the victim's body behind the counter. Okay, so the question is, I did not deal with the hearing or the seeing. So forensic architecture did separate tests about that, but I was interested in this question. He did not smell the distinct smell of gunpowder, okay? So did he or did not? So based on the timings, we have basically 40 seconds where we are accounted for. Where was he in these 40 seconds? He did something in these 40 seconds. I remember in this minute, the victim was alive, and 1 minute later, the victim was dead. So how do we do it? First, we need to define what is a smell. A smell is complicated. It's not sight, it's not hearing, it's not a spectrum-based sense. It's like you have sensors, sensory neurons in your nose that bind with certain molecules. And usually they are reactive to a certain concentration. So if certain concentration of an odorant is above a certain level, they will trigger a response in the neuron. Are very different. A smell is very different between person to person. It's also very different depending on sex, gender, age, many factors. Even a smell can saturate. If the smell is very bad, the brain will turn it off after a while, you saturate. So this is one aspect, the smell detection. But the smell at the end of the day is odorants, gases being released. These gases are being emitted by the gun. Okay. These are basically combustion products of the propellant. A gun is a propellant, which is ignited by the primer, and then the gas exit through the barrel. There are metallic particulates as the bullet goes through the barrel, and as well part of the cartridge from the primer. This forms what is called the gun shot residue, or GSR. This is what they do in the movies, and you see the gun shot residue proof in the hands, because this deposits very close to the gun. Then we have pyrolysis products, vaporization of some cartridge components, and so on. Okay, so these three are basically the emissions of a barrel. These emissions go and disperse in the room. Oops, sorry. Yeah. Okay, so a smell is basically emission of gases and dispersion. Here basically is a sketch of the problem before we go into the equations. We do have the gun injects mass and momentum. The bullet, we do not care about the bullet. The bullet goes faster and is up there. What we care is are the gases that they are dispersed around the room, and then is detected by a smell. So basically, we are looking about concentration, measuring concentration. The gas residue, which smells, okay, is a very strong smell, usually are particulates, and this deposit very, very close to the arm, to the weapon. These are often within 5 meters, usually much less. These were not considered in this study, particularly because they only affect to the floor, and usually all the smell it goes high. Remember, the gases are hot, okay, so they will rise up. So, smell plus dispersion. First, use a quick comment about odor detection. As I mentioned, smell is a tricky thing and depends on the person, but they're usually average odor thresholds, right? An average person will detect. The odor threshold is the concentration of the whatever gas that is needed to detect. So if the concentration is above odor threshold, this smell could be detected. From the gun's point of view, combustion products, remember this is not muskets, like 16th century muskets with a lot of gunpowder and a lot of smoke. These are usually smokeless gunpowders. They are called now basically nitrocellulose or combinations of nitrocellulose. So it doesn't smell. They have smelling byproducts like ammonia. Due to the primer, they may have some sulfur oxides. These they smell. But most of the smell comes from the organic compounds. They have polyaromatic hydrocarbons, PAS, and amines, and different high carbon chains. This smells. Usually you have tables and tables of other threshold values. So maybe you can have 50 or 60 gases emitted in shooting a gun. So some of them in very, very small concentrations. What we do is we define odor detectors, which is basically a normalization of the concentration of a particular component to their own threshold. Okay, and these concentrations are basically normalized as well by the psi to the exit value. The exit value is the emission factors from literature. Ideally, you should have a gas chromatography on the weapon, and that will give you these numbers. But these numbers are very, very difficult to measure. Just to make you an idea, these are usually very, very small numbers. Okay. Okay, so that's basically the smell. So we need to find out the odor detector. This odor detector, remember, greater than 1, it means you could have a smell it. An average person under average conditions. So finally, the LES. This is all done in the LES context. Okay. I guess everyone is quite familiar with LES, but just very quickly, what we do is a low pass filter to remove the smallest scales. And we assume we solve directly the large scales, and we do subgrid modeling, is called, or universal modeling of the smallest scales. Because we have variable density, we use a fabric weighted or density weighted filtering. We use a low Mach number formulation. It means the flow is compressible, but the energy equation is uncoupled from the fluid mechanics. So we solve for continuity, momentum, and passive scalar transport. This psi is this indicator that is roughly 1 at the exit of the gun, and then it disperses. The flow is turbulent, laminarizes relatively quickly. However, we still assume that all species diffuse at the same speed. This is called the unity Smith number approximation. This is fine because they diffuse in air. And remember, most of the species have very, very small concentrations. So everything is dominated by the speed of nitrogen, basically, how nitrogen diffuses. We still have a turbulent diffusion to close. We do have source terms. We do have source terms of mass and momentum, and these are driven by the gun. The gun introduces mass and momentum. And of course, I forgot gravity. This is a buoyant flow. The gases are hot, so density is also a function of this psi indicator. Reactions outside the gun are neglected, so basically, it just the moment the gun injects the gases, this is all mixing. So closures, typical of mixing. Someone know me, I came from non-premix combustion. So this is the kind of thing you will use in non-premix combustion. In this case, we use a Smagorinsky model, which is a dynamic model. The flow laminarizes. So we want to have a nice laminarization, and so dynamic model works a bit better. Subgrid mixing, we assume a gradient model for the subgrid mixing, in this case, the variance. So we need a subgrid closure of the PDF of the mixture fraction indicator. It's not a mixture. We use the beta PDF, and then we basically obtain the closure of the filter density by this integral. This is all tabulated, and to be honest, because this is linear, it's just mixing, so it's not a huge important compared to whatever are reactive flows. So even without variance, the model will work pretty much the same. Okay, so the setup is very easy. This is all done in-house in a conventional second order finite volume. We use an immersed boundary to represent moving boundaries and moving geometries. Basically, we have like a mesh. All these objects were obtained like by immersed boundaries. And there is a moment we were using an hypothesis that the door was open. The moment you open and close the door, that creates a huge change in the flow field. So we did that by moving boundaries. Of course, it's a big change in time step. So the time step close to the shooting, it was very small. There's a high momentum, and then we can change a little bit because things slow down quite a lot. Shooter position was based on ballistics. Okay, so from the police report, we know the trajectories approximated. The gases were based on ballistic analysis and data from literature. We did like some 1D analysis to get the speed and the momentum of the gun. This is basically a 1D. We use conservative estimates. You can have the pressure inside the barrel, and basically then it's like an adiabatic expansion in the ideal case. And using the composition, you can get a decent approximation of the amount of gases injected. Again, in this case, we work in the worst case scenario. We try to be very conservative, and basically, because the idea is, did he smell? So we want to say, okay, let's minimize the amount of smell dispersion. Okay. So in looking at ranges in the odor threshold, we tend to use always the minimum. I'm going to show you the video now, but the video, okay, this is a small video. That's not the one I'll show you now. This is like an idea just to give you a little bit an indication how the flow mixes, but I'll show you a much better video now. Okay, so I'm gonna this video and okay, live. This is the authentication. I'm gonna very quick. Yeah. So everyone, the video basically here is the short fire, second short fire, and you see in the book it's an isosurface of other detect greater than. Okay, so whatever, if you are inside the cloud, you should detect it. Here you see this movement is because we open the door. The opening the door creates like a huge recirculation, and then basically just lingers. The smell lingers. Okay. In this case, after a few seconds, just basically it raises up, it lingers, and basically this. Remember, this is threshold smell. If you have another top, remember big thing here. Okay, so you can see direction of the shots, high concentration of smell. Remember, this is not the smoke and this is smell. The door opens, that creates a huge recirculation, and well, the flow turns. Okay, and this is in what the hypothesis, like the suspect enters. So basically a reproduction. Okay, the idea is deep enter or so the piece back. Okay, can you see green fine? So
Salvador, I think your audio is just cracking up a bit.
Oh, okay.
It's good now. It's good now. Probably, I think,
Can
because you're playing the video. It's good now. Yep.
Okay. Yeah. So video. Yeah. So I stopped the video. Yeah. I think my computer was having many things. Hopefully not. Okay. So the idea is, if he was inside, okay, there were several scenarios, but they are all look the same. Or he was in park, he should have a smell, using all the conservative scenarios. Again, I won't comment in what happened in the trial or all these things that happen afterwards, but at least from the smell point of view, he could have a smell. Okay, so this is a second case, which I can talk much less. This is a collaboration with the Met Police and Forensic Agency and another forensic agency. It's also murder investigation. It's very similar. And the question was to assess the validity of a witness statement. Some witness says that he heard the gunshots and smelled the gunpowder immediately afterwards. There are multiple shots, bigger domain, similar methodology, different weapons, different boundary conditions, but very, very similar. There was less precision because there was no timings. So the scale is a bit bigger. I cannot go into details. Well, the house is very big. There are 3 floors, but basically it's the same. Similar map. You can see red and purple indicates odor detectors greater than 1. And in this case, you will see that time has speed up. So we are trying to do 20 minutes. So you see now, even later, it's very, very smell on the second floor. Everything in the second floor is green after a while. So what we did is, in the position of the witness, we have a tracker of the odor. Okay, and this is the odor detector. Greater than 1, it means he or she smelled it, and smaller than 1, he didn't. So here is clear that after 10 minutes, the odor starts coming up, but it never reaches above 0.05. Okay. Scenario 2 and scenario 1 correspond to different positions of the shooter, because the shooter, we were uncertain what was the original position, especially in the first shot. There were 8 shots, and one of the shots, we didn't know exactly where it was shot. Okay, so we couldn't say a lot, but still, even with the uncertainties, the number was very low. So even if some of the uncertainties are 50% or 100% regarding, for example, Odour thresholds, what we can say is the thing was not immediate. At least 10 minutes passed before the Odour arrived the witness position. Okay. So that's what we did. And oops. Okay. So what are the conclusions of this particular aspect? Okay, so we have used LES to estimate Odour dispersion. We can do things, Odour dispersion up to 30 minutes. We can do more, but it's just more expensive. And usually, unless there has been a big battle, Odour will disperse. And we can do tens of meters. Okay, these are all real geometries within mesh boundaries and so on. Again, we are not so much concerned about walls, about tiny details. So all the mesh boundaries is a bit of Minecraft kind of thing. They are not as expensive calculations, but we are all doing in parallel computing. There are big uncertainties in Odour thresholds and emission factors. So we have to be very, very conservative. Odour thresholds can be, again, I mentioned 50%, even more in certain compounds. And emissions factors are the same. Emission factors, either you measure the gun, the exact gun on the exact propellant. I think in the second case, we have the manufacturer of the propellant on board. So we have some estimates, but even emission factors depend. There have been a lot of studies published, but not on maybe on the particular gun that was used. So we have to use always an accurate, a conservative estimate. It's very difficult to have an accurate ODE, Odour detector. However, it's easy to have a qualitative one. Okay. Another limitation is we cannot distinguish smells. Okay, because we transport basically one generic marker, and then we maximize the Odour detector within compounds, and we see which one is the maximum. We can say that he or she smells something, but not what. Some witnesses say that it was a metallic smell. If you look at what people smell when they smell gunpowder, they give you all sorts of answers. Also, there is the uncertainty in the sequence of events and boundary conditions. Okay, these things are very, very uncertain. In some cases, we didn't know where the shooter was in the first shot. Okay, or how long it took to reload. Okay, it can be a very skill and reload very quickly, or it may take some time. Okay, so we always work with some hypotheses, and we always work with very conservative estimates. In the later case, we wanted to maximize that. In the first one, we want to minimize the smell. So we pick different ranges based on the hypothesis we're testing. Okay, so these are the two cases. We are all mixing and dispersion. The case 3 is a bit different. So that was a more recent. These are different country. Again, we are all changing countries. This is a case in basically in 2018. Workers, maintenance workers on a dam in France, in the French Alps, very close to Briançon. They discovered a corpse stuck in the water around 2:30. So, and basically the question, another forensic agency asked me, what is the possible or probable duration of the body's stay in the river? At first, I thought the coroner should be able to tell me that, because I am forensic, I have no idea. But apparently, it's quite difficult, especially in cold rivers. This is close to the Alps, so it's a cold river, to estimate. Especially if we are talking about the matter of hours or very few days. The victim was seen alive 2 days prior, so it's not that has been in the water for many, many days. Okay. So even if the cause of death was officially drowning, foul play was suspected. Okay, so the victim was found naked. However, the clothes were found 2 kilometers upstream. Okay, just to give you a bit of the context, this is like a map. So this is Briançon, which is like a touristic town. So usually in winter for skiing and summer for trekking. This is where the body disappeared. When there was last seen, the victim was last seen, Lavachette. It's a camping here. And this is where the body was found, roughly 2 days later. So my colleagues in the forensic agency, by interviewing witness, basically they got an idea that the victim disappeared at 4:30 and was found next to 2 days later here. The clothes were found upstream of the disappearance position. Okay, so that's very difficult problem as the a priori. So as an engineer, I asked, what is my context? What can I do? I have details of the river, and there is some dams in the river. You can see here the size of the river. Okay, a little bit. How is the configured? This is one of the dams. There are several small dams. It's not a big river. It's relatively small, narrow. It's not one of these mountain rivers, but very close to. We have an idea of the flow rate, the river depth. So it's not very deep. But people, I mean, if the river is fast, people can drown in such a small river. And we have like a sequence of events. This is estimated from the forensic agency. Basically, we have an estimated time based on witness reports when the victim entered the water. Was 4:30 in the morning, and they got an idea of where the body was found, basically. And there are also two key things. The main dam was cleaned the day in the middle, and also the second day. So they have a periodic. So basically, the key thing is, okay, I need to model the river and then model the transport of the body. Okay, so modeling the river. So equations. My idea, of course, is to throw LES of everything, but this cannot be done with LES. Okay, so this is the kind of thing you cannot do. We are talking about 12 kilometers, a bit more, and it's a narrow river. So we're talking about 10, 20 meters in the narrowest of the 12 kilometers. So we couldn't do 3D. So what we do, we use the 2D shallow water equations. Basically, we got the 3D Navier-Stokes equations, depth average. So we introduce the depth of the water, H. So we have 3 2D equations. We need to include the bed stresses. So basically, instead of pressure, we have a hydrostatic pressure, basically the slope. So we do have the bathymetry of the river. We do have the shape of the river. They provide me with all this. And okay, basically this Manning resistant, which is the river bed stress, we do have a Manning coefficient. So that depends on if it's very sandy riverbed or it's very rocky. So this basically accounts for how rough the river is. We need to add a turbulence model. Fine, we add one. In this case, algebraic model was fine. We validated this by comparing about the depths that they measured the dam. So we were quite okay that at least we got very similar results. We know the depth of the river, the initial point, and we got very similar depth. So it's okay. We ignore certain small affluents. We have to, because we cannot do everything. And some bit bigger affluents were just added like a source of mass. We assume that the body was not going to go upstream on affluents. Not sure that adding more detail will add. I mean, this is still very uncertain. Okay, so this model tends to work better in bigger rivers and with sandy. But that's what we have to do. We have to ignore boulders in the middle of the river and arches in the bridges. There are certain bridges when the river passes through towns. So we have to ignore them from the flow field because we didn't have all the details. And we incorporate that in the collision model. I'm going to explain in a bit. The river changes slope. So before Briançon, it has a bigger slope, and then it goes to Briançon, and then it opens up a little bit and becomes wider. So, okay, so we did a bit of stochastic modeling because, I mean, it's clear that tracking one body is going to be very inaccurate. So what we did is, okay, let's look in a statistical sense. What is the probability of the body arriving? Or if you want to be more precise, let's try to find an equation for the probability of a body being in a certain position and have certain velocity. So I don't know how familiar are you with the stochastic models, but basically it's possible to derive a PDF transport equation, which is a transport equation in 4 dimensions. It would be a space, time, and velocity. 1 and 5 would be 7. And to obtain the evolution of this PDF. The acceleration of the body, we can decompose into a deterministic part and the gradient of a stochastic component. But basically, this is the diffusion. So we arrive with a Fokker-Planck type equation, which is a drift coefficient by the velocity in a space, by the acceleration in velocity space, and some diffusion coefficient. Basically, the body, because the flow is turbulent, it won't follow the streamline exactly, even if the drag allows to, it will deviate, okay, due to this stochastic component. Once you have a Fokker-Planck, then there is a state equivalent. We have 2 sets of SDEs, dx and dv, which they look like a particle. Those of you who have done particle simulations, they look very similar. And the only thing is we have here an stochastic diffusion term. Okay, this term, it correlates with the turbulence of the fluid. So basically, this is the turbulence, if you want. Okay, great. We have all this. So instead of solving one body, we solve n bodies, in this case, thousands of bodies, and stochastic trajectories. And we see what happened with the stochastic trajectories. The body itself, the equation is relatively simple. We allow the body to move and has a relative orientation. The bodies are modeled as partially submerged cylinders. Okay, that was the easiest way to model. The key thing here is that the body is allowed to collide with boulders and with arches. And basically, we group all these using a Poisson process. So every now and then, with an expected rate, the body will collide and it will change trajectory and will lose a little bit of energy. How we estimate the collision rate? So basically, we look about the number of obstacles in the river. That day, it was after several days of raining, so there was a lot of debris in the water. Okay. So, and remember, this is a mountain river, especially upstream. So upstream, there are certain amount of boulders in the middle. So looking a little bit, we define, okay, we can have a very low collision rate. Imagine one obstacle every 25 square meters, defined by looking at photographs. That would be a low estimate. And our high estimate would be where there are very, very lots of obstacles. Okay, so we can consider 2 extremes. I mean, the body was found, it had lacerations, then abrasions, so there was a lot of, he has definitely gone through some collisions. There was a lot of collisions in part of the body, but not in the back, so the body was usually lying down. Okay. So we simulate 2,000 bodies. We have a mesh resolution around a meter, depends. We allow the body to rotate to align. And yeah, and I'll show you some results. Okay. So this is basically the river. It's very difficult to have a nice, colorful presentation because they're just basically bodies moving. No, there is no, as before, very nice presentation. Okay, so this is roughly 10 hours after the body was supposed to be here in Lavachette. These are bodies colored by velocity. Oops, sorry. So you can see some slow bodies are still in the upper part of the river. However, some fast bodies have gone all the way through the dam. The dam is in place. Okay. After 23 hours, only a few bodies are still stuck in the river. These bodies are very, very low velocity. And what happens? They got stuck in the river. Due to the stochastic, there is a small probability that these bodies may get unstuck. There is a tiny fluctuation of turbulence, and they are lucky on the draw, these bodies may get unstuck. Remember, even they look that there is a lot of bodies stuck. Here you have like a big body of 1,000 bodies piled up in the dam. What is the idea is not looking at this doesn't tell you much, is look directly at the PDFs. So these are the two scenarios, one with low collision rate and the other one with high collision rate. And this is the probability of arrival time to the dam. So let's look at the low collision rate. The low collision rate, there is a big chunk of body, more than 50% of the bodies arrive at the dam around 9 a.m. the same day. Okay, and then there is like a tiny probability distribution of bodies arrive. Okay, there's a very few probability that the bodies arrive after the first cleaning of the dams. So this scenario was deemed unlikely. Why? Because the maintenance workers say that the body was not there when they cleaned the dam. Okay, so all of these bodies arrived before the dam was cleaned. Remember, the body was discovered later. So in the second scenario, there is a high rate of collisions. We still have a big bunch of speed bodies. However, they arrive much later, the 2 p.m. in the afternoon, the next day, the 7th of May. However, there is a big tail of bodies arriving. Remember, the blue bar indicates when they clean the dam, but there's still a lot of probability of the bodies arriving after they clean the dam. So this scenario, it's possible that the body arrive past the dam, arrive after they clean the body. Okay, after they clean the dam. However, these bodies would have suffered many more collisions because their bodies, they are slow because they're impacting the riverbed, on the boulders, many more times. And probably the body would have seen many more lesions. So for this reason, scenario 2 is not very likely as well. It's because in a pickle. Given the witness report, I don't know what of the two things happened. And anything in the middle, the fact that they cleaned the dam the 8th of May makes me meet a bit very difficult. Also, you have to remember if the dam was here, if the body arrived here, this is the day. And this is not a very hidden dam, and it's not very big. Be that the dam spent 24 hours being hidden, but it's still unlikely. So we are not clear what happened, these things. So what I try to do is I try to do some reverse calculations. If I know where the body arrived, can I reconstruct the point of entry by reversing the equations? So I did the same. So instead of putting the bodies in, at the beginning, I put the bodies at the end and see where they could have. This, of course, is not very accurate because as far as you go in the past, the wider dispersion and uncertainty, there are river meanders. So basically, the bodies concentrated. So it's not a very precise, so we still need to refine a little bit this. So in this case, we cannot conclude. Okay, so basically that's everything. I'm looking at my time. Yeah, I think it's time. This is a very multidisciplinary field. Okay, hopefully I have given you a taste of, I would say, new applications. They all have a combination of dispersion, mixing, turbulence. They all share the same unsteady and unreliable boundary conditions, uncertainty, Odour thresholds, collision rates. They are still very uncertain because it cannot be never accurately known. We always work with conservative estimates, or we have two extremes of the scenarios, very high collisions, very low collisions. All these cases were scenario testing. So we have one scenario, we say this is likely, this is unlikely, and we test it. Okay. There are a few cases of CFD applying to forensic science, but they still believe or think that CFD has potential to help. It's rare. I'm not gonna make the living out of this. These are rare, but I think I foresee CFD having a bigger potential. And it won't tell you who did it, but it might help you, giving you a better picture to understand what happens. So that's it. Thank you for your attention. And if you have any questions, I'm happy to share. Yeah.
Thanks, Salvador.
Stop.
That was an amazing talk. It felt like I was in a thriller movie waiting to know what's going to happen next.
Okay.
Anyway, I'll open the floor up for questions. So anyone from the audience, if you have a question, please feel free to unmute and ask, or type it in the chat and I'll read it out, or Salvador can have a look in the chat. All right, while the audience is gathering their thoughts, I had one question. In the first case, you said that, I remember you mentioned that there was an information that a silencer might have been used with the gun.
Yes.
Did you factor that in your analysis? Because that would change the way the plume comes out of the gun.
Yes, yes, we thought about that. In fact, some of the suggestions were saying that the gun was shot inside the bag. So the weapon was inside the bag and was shot from inside the bag. We couldn't only do like a source of mass or momentum. We couldn't have the details. Yes, the plume will be slightly different, but the amount of mass you will inject is the same.
Yeah.
I mean, at the moment you have a hole, the gases will exhaust. This is not accurate very close to the gun matter because they don't have the resolution. But, there is no way to account from that in a very precise way. We could only account of, okay, we add mass and see what the dispersion is.
All right, okay, thanks.
Yeah, need more points. Else.
Any? With in the just before your conclusions, you said that you did a reverse calculation as to
yes,
you factored in when the body reached and then you worked backwards. What did you find from that?
Okay, so that's the thing. I do have on a slide, but
all
it's not,
right, okay.
Yeah, the problem is the trajectories. You're trying to do the inverse, but it's a stochastic calculation. So the further you go in the past, the more will open. So basically, there's a moment that the body could have entered nearly everywhere. So they were uniform. There are points where there is high concentrations of points of entry, but one of them was very close to the road in a very, everyone could have seen it. I use very odd. And the other one was a meander. And the moment you have like a meander, the pictures will converge, use the sense. So it's not, I don't think my confidence was lower in this analysis. So I just, some ideas, I haven't seen this sort of reverse calculations done. Maybe I need to know more to have confidence.
Any other questions? Any questions from the audience? No? All right, then please join me in thanking Salvador for an excellent talk. And thank you all for taking our time so late and joining the seminar. Thanks, everyone.